Okay, so today what we're going to talk about is limiting reactants. And so here's the idea. If you have a recipe, just because you have the recipe does not mean you're going to have exact quantities of the things you need. So if you had to have 1 cup of flour and 1 cup of sugar, because I don't know what mix what you're making with that, but let's say that's your recipe. So flour sugar is what you're making, right? Just because you have that recipe does not mean you have that amount of flour and or sugars, particularly now with the way stores are. So you might have 10 cups of flour and only 5 cups of sugar. And if you follow that recipe of 1 cup of flour for every 1 cup of sugar, do you realize that eventually you'd run out of sugar, right? And then you couldn't make your flour sugar anymore. And that's the same thing that happens with reactions. I want you to take a look at your video notes here. And the term that we use for the thing that gets used up in a reaction, we call that the limiting reactant. So the reactant gets used up first when we're doing a reaction is called the limiting reactant. And the reactant that gets left over is called the excess reactant. Now, it's also kind of important that a lot of the reason that we care about whether or not one of the reactants is going to get used up is because when one of the reactants gets used up, the reaction stops. So if we ever want to figure out the amount of product in a reaction, which we sometimes call the theoretical yield, they make words really hard for us sometimes. I'm going to write yield down below here because I did not space myself very well here. In order to figure out the theoretical yield, you must always start with the limiting reactant, because the idea is simply this. When you run out of something, your reaction stops, and therefore the amount of product you're going to get is going to stop as well. Now here's a pretty simple example. Let's say there's an airliner that has 350 seats. Let's call it United, because they do this often. They had a practice prior to now of they would overbook their seats by a lot. Let's say they'd say, all right, there's 400 people, but they've sold those 350 seats to all of them, right? Here's the thing though. In this example, there's only 350 seats, right? So guess how many people are getting on the plane? Only 350, right? So even though we have excess people, we have a limited amount of seats. So in this case, the seats would be my limiting reactant. I'm going to abbreviate that as LR, and the people would be my excess reactant. A more appropriate example nowadays would be this. We have 350 seats, and we have 3 people that evidently have no fear of consequences or anything happening, wanting to get on the plane. And in this case, very clearly, this would be my limit. This would be my limiting reactant, right? Because 350 seats are just going to be excess. Yeah. Now, I could go on about airplane examples forever and ever, but mostly because my son is enthralled with airplanes. But let's take a look at an example in actual chemistry lab. So if I take a look at this, and one of the things I want to remind you of is that all of our equations are written in moles. So if you want to just jot this down somewhere, written in moles. So when I read this, what it says is you need, remember there's a coefficient right here of a 1, right? Even though it's not written. There's a 1 here, there's a 1 here, and there's a 1 here. Although that looks kind of like a 2. Let's make sure that that's a 1. I think that made that much, much worse. But if I were to tell you, hey, I'm giving you 5 moles of carbon and 10 moles of oxygen, and I asked you which one of these is the limiting reactant, if it's a 1-to-1 ratio, would any of you have any trouble with this? I'm hoping not, because the reality is if we have a 1-to-1 ratio, I'm going to use up 5 moles of my oxygen. Wouldn't that react with 5 moles of the carbon? So the oxygen would react with 5 moles of the carbon, but then wouldn't I still have extra 5 moles of oxygen? Now, does that kind of make sense? I'm asking to a video that can't respond. That's kind of cool. So in this particular case, since it's a 1-to-1 ratio and I have 5 moles of carbon and 10 moles of oxygen, the 5 moles of carbon, that would be my limiting reactant, and the 10 moles of oxygen would be my excess reactant. Now, you need to be really careful here because this recipe is a 1-to-1-to-1 ratio. That's why we can compare the number of moles of this and the number of moles of this and say, well, we have less moles of this, so therefore this is my limiting reactant. But if the ratio isn't 1-to-1, we might need 5 times as much carbon, and in that case, or 5 times as much oxygen. In that case, the oxygen can be a limiting reactant. So I'm going to give you some steps here to how to figure out a limiting reactant from a problem, and I want you to kind of fill this in. But the most important thing that I can remind you of here is that whenever you're doing a limiting reactant problem, you must have a balanced equation. If you don't have a balanced equation, you cannot solve any problem. Now here are the steps. Convert both reactants into moles if they aren't in moles already. Now here's the thing. I don't know if you have a molimeter around your home or anywhere, and in the lab we certainly didn't have a molimeter, but we did have scales. This is me interpreting a scale. So when we put something on a scale, it would measure in grams. So often what will happen is we'll have an equation that's written in moles because, all equations are written in moles, but they'll give us grams. So the first step is going to be to convert from grams to moles in every type of problem. Now here's the cool, and this is actually a really neat thing. I actually learned how to do this a few years back. And here's the trick. When you have the moles of each reactant, you're going to divide the moles of each reactant by the coefficient in the balanced equation, and whatever number is lowest is the limiting reactant. Now, clearly the best way to do this is to do a problem, so let's try a problem. We're going to try it the highest difficulty possible because if we can do a highest difficulty problem, we'll be able to do any type of problem. So let's take a look at this problem right now, and if you take a notice here, you might have thought we were going to jump right into the steps here up above and convert both the reactants to the mole, but there's a step beforehand that says you must always have a balanced equation. So let's take a look at this and see if this is truly a balanced equation. If we have 2 hydrogens here, we also have, let me make sure my pen is working here. We have 2 hydrogens here. Do you see we also have 2 hydrogens here? That's okay, that's balanced. We have 2 oxygens here. Do you see we only have 1 oxygen right here? So that means we have to put a coefficient of a 2 in front of this. But when we do that, don't we have, now when we multiply this out, don't we have 4 hydrogens? So don't we have to put a 2 in front of this as well? So now we have a balanced equation. We're going to go to step 1, and step 1 is convert both of these reactants, both this reactant and this reactant, into moles. Now you cannot look at this and go, oh wait, I have 32 grams of oxygen and 8 grams of this, therefore I'm going to run out of hydrogen first. You can't do this because this is a mole ratio equation and this is grams. So let's take a look, and first step we're going to do is convert it into from grams of oxygen, we're going to convert to moles of oxygen. Now, I don't have the periodic table here in front of me, but what we can do is we can pretend that we have a periodic table, because I've done this before, a few times, not my first rodeo. And if we do have a periodic table in front of us, oxygen underneath it would say 16.00, and hydrogen underneath it would say 1.008. I want to point out something here to you, because you might be inclined to go, oh yeah, we have oxygen, and write 16 underneath here. But do you see how we have O2, which means we have 2 oxygens, right? And if we have 2 oxygens, wouldn't we have to multiply 2 by 16.00 to get our molar mass, which is going to be 32.00 grams per mole? And let me remind you that when we have 32.00 grams per mole, we can write it that way, or we can write it as 1 mole per 32.00 grams of O2. Now, in this case, of these 2 choices, we're going to put the 32.00 grams of O2 on the bottom and the 1 mole of O2 on the top, because we want to cancel, as always is the case, we want to cancel out our units on the top. So we have grams here and we have grams here, and they cancel. And when we do the math, we're going to end up with 1.000 moles of O2. All right, let's do the same thing now for hydrogen. We have 8.064 grams of H2. Well, similarly, we have 1.008 here, but for H2, wouldn't we have to multiply this by 2? And if we did that, wouldn't we have 2.016 as my molar mass for that? True story? So if I have 2.016, I'm going to write 2.016 grams of H2 on the bottom, and I'm going to have 1 mole of H2 on the top, which again allows me to cancel out grams here and here, and I'm going to end up with moles. And when I do the math, again, I kind of finagled the numbers in advance. I'm going to end up with 4.000 moles of H2. Now, just so you're aware, they will never work out this perfectly, but here's the trick part, and this is really super cool. Step 2 is this. Once you know the moles of each one, what you can do is you can take the moles of each one, 1.000 moles of O2, and you can divide it by the coefficient. Now, if you take a look at the coefficient here, isn't it 1? Now, typically what I'll do in a problem like this, if I was doing it normally, I would go like this. I'd put the coefficient underneath here, and I would end up with the number 1. And this number right here is our trick number that lets us know that we're going to compare against the number we get right here. Similarly, if I have 4.0000 moles of H2, wouldn't I divide that by its coefficient, which happens to be 2? So if I'm dividing that by 2, and again, I'm going to show you how we could just do it underneath here, divided by 2, wouldn't my number here be a 2? So all we're going to do then is compare these two numbers. Whatever number is smaller, that means that the original that we started off with is the limiting reactant. And so this number is smaller, so therefore this is my limiting reactant, and this is my excess reactant. I did the cool way of writing it with an X instead of E. And that means that my 3.00 grams of oxygen is my limiting reactant, and my H2 is my excess reactant. So we will definitely go over more of these types of problems in class, but hopefully this has been helpful, and thanks so much for watching.